Wave functions live in Hilbert spaces. So if we want to understand a quantum mechanical wave function or a quantum state, it is better if we have some kind of an idea of what a Hilbert space is. Mathematically speaking, a Hilbert space is a linear vector space with a well-defined inner product, a norm that is positive, and a space that is complete. Now these are four very important criteria, and therefore we need to understand them one by one. And to understand these criteria, I'm going to be using a couple of examples from mathematics of different kinds of mathematical spaces. And we will use these examples to get a better idea of what a Hilbert space is, because it seems that Hilbert space, at least the topic of Hilbert space, seems to be very, very abstract. But it did not be very difficult to understand. So to understand, first we need to explain what a linear vector space is. A linear vector space consists of two elements, vectors and scalars, and it has two mathematical operations, vector addition and scalar multiplication. That's it. What is a linear vector space? So Hilbert spaces are linear vector spaces. And as I just now said, linear vector spaces consist of two distinct elements, vectors and scalars. Now, here I need to make one very important distinction, that when I say vectors, I do not necessarily mean geometrical vectors, because till this point in time in school and college physics, we are only used to vectors as these kinds of lines or arrows having a magnitude and a direction. What we are doing right now is we are taking these concepts of vectors into a much more abstract form. So when I say vectors here, I do not necessarily mean 3D vectors, even though it is a linear vector space, but in mathematics we can have various other kinds of vectors as well. So here vectors and scalars comprise of the linear vector space if we also associate two mathematical operations in this space. First is vector addition and second is scalar multiplication. Now depending upon the mathematical space, the vectors could be elements which have their own peculiar properties, but scalars are usually taken to be real numbers or complex numbers. So whenever we say scalars, we usually by convention take the real number space, which is basically 1, 2, 3, 4 rational numbers, fractions, integers, negative, positive numbers, irrational numbers, etc., and complex numbers. So it depends that we can sometimes define vector spaces over real number space or sometimes over complex number space. And let's say that we say that the vectors themselves are represented by alpha, beta, gamma, etc. Okay. Now here I'm using the Dirac notation, the ket representation, but it is not necessary to use the ket representation because we are studying this topic in the context of quantum mechanics. Therefore, I'm using the Dirac notation. But in general, the Dirac notation is not necessary. In mathematics, you could just write alpha, beta, gamma, just like that to represent vectors here. Of course, when we talk about three-dimensional Euclidean vectors, there the vectors are written with an arrow at the top. That's a very specific symbol used for geometrical vectors. Here we are going to be using ket representation to represent the vectors, and scalars I'm going to be using as A, B, C, where A, B, C, these are numbers that belong to the real number space for the time being. Now what a linear vector space is a space which is closed under these two operations. That means if I take two vectors, let's suppose alpha and beta, then the final vector that I get, let's suppose I get gamma, must also belong to the original space. That is called closed under vector addition. And similarly, if I take a scalar, let's suppose A, and I take a vector, let's suppose alpha, and if I get another vector, let's suppose eta, then that vector must belong to the original space. This is known as the closure property. So a linear vector space must be closed under the mathematical operations of vector addition and scalar multiplication. Now, let's take an example. For example, rational numbers and real numbers. Okay. Now, you probably understand the distinction between rational and real numbers. Rational numbers are positive numbers, negative numbers, natural numbers, whole numbers, integers. Anything that can be represented in the form of a fraction. All of these are rational numbers. Real numbers, on the other hand, are rational numbers, but they also include irrational numbers like square root of 2, square root of 3. They also include non-terminating numbers like pi, etc., etc. Now, if I take rational numbers and I consider all the rational numbers as vector elements belonging to certain kind of a space, and I take the scalars, as I said, by convention, we usually take the scalars to be real numbers. Then if I multiply, let's suppose, root 2, which is an irrational number, which is a scalar, to some kind of an element of the rational number space, let's suppose 1, then the final result is an irrational number. That means, so if I take an irrational number, multiply with a rational number, I end up getting an irrational number at the end, which means that the rational number space is not closed under scalar multiplication if we assume scalars to be the real number space. In that context, rational number space is not a linear vector space. Of course, there is an exception that if we do not consider the real number space as a scalar, but rather if I consider only the rational numbers as the scalars, in that particular situation, it will be a linear vector space. But of course, that kind of a situation is not very important for us. We usually take real numbers as the scalars here. And in that context, rational numbers do not satisfy the closure property of scalar multiplication. I hope that makes sense as to what all of this means. Now, the moment I define these two operations, we end up getting few other related to this. For example, we have the property of commutativity, which means that the order of the sum of two vectors is not important. That means alpha plus beta is equal to beta plus alpha. So for example, if I look at 3D Euclidean vectors and I have two vectors A, and let's suppose I have another vector B, which is basically equal to bx I cap plus by j cap plus bz k cap, then A plus B is equal to B plus A. So it means it is commutative with respect to vector addition. Also, there is a property of associativity, which means that if I add a vector alpha to the sum of two other vectors beta plus gamma, this is equal to the sum of the vectors alpha and beta added to the vector gamma as usual. We can also define a null vector here. That means if I add a vector alpha to another vector so that the resultant vector is alpha itself, then that vector is nothing but a null vector. Similarly, we have inverse vectors, that if I have a vector alpha, there must be an inverse vector minus alpha such that the resultant is a null vector. Now, these are some of the properties as a result or as a consequence of the mathematical operation of vector addition that elements belonging to a linear vector space must satisfy. Similarly, for scalar multiplication, we also have some additional properties of distributivity. So the scalar multiplication is distributive, which means that if I have a scalar multiplication of A to the sum of vectors, let's suppose alpha plus beta, then this whole expression can be written as A times alpha plus A times beta. Similarly, if I have the sum of two scalars A plus B being scalar multiplied to something like beta, I should get A beta plus B beta. Now, of course, these kinds of operations may look very trivial to you, But you have to understand that we are trying to come up with a very abstract space with certain kinds of properties that needs to be valid, properties of various mathematical operations, and then we need to be able to check if those properties are satisfied by different kinds of mathematical spaces. And because we are studying quantum mechanics, the quantum states also belong to a Hilbert space. Therefore, quantum mechanical kets or quantum mechanical states also satisfy these kinds of properties. So a Hilbert space is a linear vector space which essentially consists of vector elements and scalar elements which are either real numbers or complex numbers, and they are closed under the mathematical operations of vector addition and scalar multiplication. But that is just one of the property of Hilbert spaces. The next property is that of inner products. So a Hilbert space must have a well-defined inner product. Now, what is inner product? Let's go back to our original geometrical vectors. When we study geometrical vectors, there is one particular multiplication that is very common, which is that of the dot product or the scalar product. So if I have two distinct vectors, let's suppose this is A and I have another vector, let's suppose B, then I can easily define something like A dot B, and you guys know that A dot B is essentially the sum of the product of the respective components of A and B along the x, y and z direction. So that means I end up getting AX BX plus AY BY plus AZ BZ. It is a very simple kind of a mathematical multiplication operation that is only valid in geometrical vectors. So when I have two different geometrical vectors, the scalar product or the dot product is written in this particular manner. This kind of a dot product can give us an idea about whether these vectors are perpendicular to each other or not. It can also give us an idea about the length of a particular vector. It can also give us an idea about the relative directions or the projection of one vector with respect to another. This whole idea is generalized into the more abstract sort of a concept called inner product. So when we come out of this geometrical vector space and we talk about linear vector spaces in general, we can define something called an inner product, which is a much more abstract generalization of the concept of a dot product in geometrical vectors. So if we have two vectors, alpha and beta, let's suppose, then we can define an inner product in this particular manner in Dirac notation, or in general sometimes it is also written as alpha comma beta within brackets. This is simply the representation of an inner product. How the inner product is defined depends upon that particular vector space, but this is how an inner product is represented. And if the vectors are spanning the real space, then the inner product is a real number. And if the vectors are spanning a complex space, then the inner product could be a complex number. Therefore, an inner product of two vectors belonging to a linear vector space, when we switch or rearrange the order of those vectors, let's suppose the inner product of beta and alpha, then we take the complex conjugate of that particular inner product. So the moment we switch the places of the vectors, we take a complex conjugate if these vectors are spanning a complex space. Otherwise, if the vectors are spanning a real space, then they are both going to be equal. So we can define an inner product between two elements or two vectors belonging to a vector space or a linear vector space in this particular manner, and the inner product of one vector with itself is always greater than equal to 0 unless we are dealing with a null vector. Unless we are dealing with a null vector. So if alpha is a null vector, only in that situation the inner product would be equal to 0. So you can see that this is how the inner product is defined, which is also true for quantum states. So when we are dealing with quantum states, so we are dealing with kets and bras representing the wave function state of a quantum mechanical system, we can find the inner product in this particular manner. But to get a better idea of what these inner products are, here again I have a list of examples, right? We already went through rational numbers, and I think by now it's also clear that the real number space is closed under operations of vector addition and scalar multiplication. So at least real numbers can be considered a trivial case of a linear vector space. Alright. But we have some other examples here. We have complex number space, we have 3D geometrical vectors, we have polynomial space, which is defined between -1 and +1, we have square integrable functions. Now, complex numbers is something you are familiar with. We usually extend the real number line with an imaginary line, and then we can create various complex numbers in that particular space. 3D Euclidean vectors is also something that you are familiar with. We connect 2 points in 3D Euclidean space that gives us an idea about the length between those 2 points and the direction that is represented by the arrow between those 2 points. Now, polynomial space is an interesting space. It essentially consists of various kinds of polynomials. Here I've written a very general representation of a polynomial. If I define various kinds of polynomials in a given space, I can have a large number of polynomials like x square, x cube, x to the power 4. Various kinds of polynomials are possible in a given particular range, and they also represent a very genuine case of a linear vector space. The last example is that of square integrable functions. What are square integrable functions? And specially defined in a particular region, square integrable functions are those functions whose absolute mod square integration in a region is less than equal to infinity. And there are different kinds of functions that satisfy this particular property. For example, a Gaussian function, oscillating functions, these are all square integrable functions because if I take the mod square of that function and integrate in a given range, it should always come out to be less than infinity. And those kinds of functions also represent a very particular mathematical linear vector space. So coming back to inner product, I can define an inner product for all these cases that satisfies these properties. For example, if I take a real number, then I can easily define an inner product of two real numbers, let's suppose x and y. So let's suppose x is one real number, maybe 1, 2, whatever you want to take, and y is another real number, whatever you want to take. I can define an inner product of those real numbers, and I say it is simply equal to the multiplication of those two numbers. That's it. That's it. It's a very simple example of an inner product that I took two real numbers, any two real numbers, and if I define the inner product in this particular manner, then that's a well-defined inner product for a real number space. Same way, we can also define an inner product for a complex number. So if I have a complex number, let's suppose z and w, let's suppose. Now I can also define a complex number, let's suppose z can be written as z1 plus iota z2 and w1 plus iota w2. These are complex numbers, but if you remember, I just now mentioned that if I switch the order and of the inner product for those vectors that span a complex space, then I have to take the complex conjugate, which means that the inner product is defined in such a manner that I take the complex conjugate of the first term here. Now usually in quantum mechanics we take the complex conjugate of the first term, the left hand side term, but there are certain kinds of mathematical operations outside the context of quantum mechanics where it is taken for the second particular term. I can also define inner product for geometrical vectors, which I already defined, a dot b. What is a dot b here? For geometrical vectors, a dot b is simply defined in this particular manner: ax, ay, az as a row vector, and let's suppose bx, by, and bz as a column vector. I can also define for square integrable functions. So the inner product for square integrable functions, let's suppose I have a function f and I have a function g. The inner product of those two functions is defined as you take the integration of f star g, you integrate with respect to x. X goes from, let's suppose, 0 to a. This is how a square integrable function inner product is defined. Again, polynomials also I can do the same thing. Here I've taken a very abstract polynomial px, which is equal to a0 plus a1x plus a2x square plus an x to the power n. If I imagine that I have px is one polynomial and gx is another polynomial, then the inner product can be defined in this particular manner. You take px, multiply with gx, dx, and then you integrate between -1 and +1. Of course, if the polynomials span the real space, then I don't have to do anything, but if the polynomials span the complex space, then I take the complex conjugate for the first term. This is how we can define an inner product for all these different examples, whether real numbers, whether complex numbers, whether 3D Euclidean vectors, whether polynomial space, whether square integrable functions. So a well-defined inner product is very, very necessary for us to define a mathematical space as a Hilbert space. But the moment we define an inner product, we come up with other kinds of concepts. Concepts related to orthogonality, concepts related to length. So this leads to the third important criteria for what Hilbert spaces are. Hilbert spaces need to have a positive norm. What does it mean to have a positive norm? Well, you see, when we talk about the dot product of Euclidean vectors, we can always find the dot product of a vector with itself. Right, so for example, if I want to find out the dot product of a vector A with itself, A dot A, this is simply nothing but AX square plus AY square plus AZ square, right? What does this tell us? It simply tells us about the length of that particular vector. So the norm is essentially an abstract concept that generalizes the concept of a length of a given vector. That's it. So if you can take the inner product of a vector with itself, the norm is simply the square root of the inner product of that particular quantity. So for example, if I take a vector alpha and I find the inner product of the alpha with itself, then if I take the length of that particular quantity, it is written as the norm, which is essentially the square root of the inner product of the vector with itself. And for a mathematical space to be a Hilbert space, this norm must always be positive. So whether you deal with usual 3D Euclidean vectors or whether you deal with other kinds of mathematical spaces, if I have a well-defined inner product and I take an element of that particular space and I do an inner product of the element with itself, the square root of that must be greater than 0. If that is possible, then it satisfies the third important criteria of that particular space being a Hilbert space. Now, by now, you must be sort of correlating all of these things with the quantum states. If you're doing that, you're doing a very good job, because all these properties that I'm mentioning here for abstract elements is all applicable for quantum mechanics, because in quantum mechanics, the wave functions or the quantum states all satisfy these kinds of properties. Now, the last and the necessary criteria for a particular space to be a Hilbert space is something which is called completeness. A Hilbert space must be complete. Now, what is the meaning of completeness? Now, I'm going to be talking about the property of completeness, and there is another property called separability, and these two are highly mathematical concepts. So I'm not going to be using mathematical definitions here because we are physicists. I'm simply trying to give you some visual, some easy to understand analogy for these kinds of criteria so that you get a better understanding of what the quantum states are. So I'm trying to avoid extremely detailed mathematical definitions, but still I'm going to give you sort of an analogy of what completeness means. You see, Hilbert spaces are complete. Mathematically, a Hilbert space is complete if all Cauchy sequence of the vectors in that space closes on a vector belonging to that space itself. Now, what is a Cauchy sequence? A Cauchy sequence is simply a sequence of vectors in a given space that comes closer and closer to one another as the sequence progresses. For example, here I am walking on the ground in my house. Okay. Now, if I create a sequence of events, for example, If I take a step and another step in such a manner that the second step is shorter than the first step, and the third step is shorter than the second step, and the fourth step is shorter than the third step, I've essentially created what is called a Cauchy sequence. Let me repeat that again. I take one step in front of me, and then I take another step which is shorter than the first step, and then I take another step which is shorter than the second step, and then another step which is shorter than the third step, and on. I have essentially created what is called a Cauchy sequence. And I can create a Cauchy sequence of these vectors, and I can see whether they converge into a vector belonging to the original space or not. If the Cauchy sequence converges onto the original vector space, then we end up getting completeness. If it doesn't, then we do not end up getting completeness. For example, let's suppose the rational number space. Now in the rational number space, let me take a rational number 1.4. This is a rational number because I can always write it in the manner of a fraction. Now let us make it part of a sequence where the next number is 1.41, which is also a rational number. The next number is 1.414, which is also a rational number. And the next number is 1.4142. You see how the sequence is progressing forward? These are all rational numbers coming close to one another as we go forward in the sequence. But if you look at the nature of this particular sequence, it finally converges on what? It finally converges on root 2, the square root of 2. So if the sequence progresses forward in this particular manner, it finally converges on square root of 2. But square root of 2 is not a rational number. So essentially, I have a Cauchy sequence of rational numbers that converges on an irrational number. That means rational numbers do not satisfy the completeness theorem. The same can be said about pi. I can take a rational number 3.1, 3.14, 3.141 and on, which finally converges on pi, which is an irrational number. Therefore, rational number space is not a complete mathematical space. I'm going to use another example now. The example of polynomials in a given space of -1 to +1. Now, I just mentioned that polynomials are essentially written in this particular manner, right? And we can always represent polynomials as curves in a given space. Now, let's say I take a parabola, which is essentially x square, right? You know what an x square parabola looks like. But what if I take a little bit higher terms and I add those higher terms to x square so that this parabolic curve sort of becomes more and more sharp in the edges so that it finally approaches a function which is the mod function. Now what's happening here is that we have polynomial curves, and I've created a sequence of polynomial curves coming close and close to one another such that they finally converge on the mod or the absolute function. But the absolute function is not a polynomial. So I have a sequence of polynomials belonging to the polynomial space converging on a function which is not a polynomial. Therefore, the polynomial space is not complete. Are you understanding what's happening? So completeness means that you take any kind of a vector space, you take a Cauchy sequence, which is essentially a sequence of vectors coming closer and closer to one another, which finally converges on a vector. If the final vector belongs to the original space, you have a complete space. Otherwise, you do not have a complete space. And in that sense, 3D Euclidean vectors, complex numbers, real numbers, and square integrable functions are all complete spaces. Now, these are the main criteria of whether a particular mathematical space is a Hilbert space or not. That it is a linear vector space that satisfies the conditions of closure property with vector addition and scalar multiplication, that it has a well-defined inner product, that it has a positive norm, that it is complete. If these conditions are being satisfied, then that kind of a mathematical space is a Hilbert space. Now, there is one more property that I would like to elaborate before I wrap up this video, is the property of what is called separability. Now, separability is not sort of a necessary criteria for a space to be a Hilbert space, but the reason I'm mentioning separability is because in quantum mechanics, the Hilbert spaces that we deal with are actually separable. So that's why I want to mention what separability is. You see, in quantum mechanics or in mathematical spaces, we are dealing with a lot of vectors, right? Vectors which are very, very close to one another. Vectors that can be constructed from one vector can be constructed from the others. Now, separability simply means that can we construct all the vectors of that particular space from a countable set of fundamental vectors. So a linear vector space is separable if it is constructed from a dense but a countable set of basic elements or basic building blocks. In that situation, it's called separable, but if the vector space is too large and too irregular for us to create a countable number of fundamental building blocks, then it is non-separable. For that, we have a couple of examples. So the English language is constructed by the English alphabet, which are essentially 26 countable distinct alphabets. Using them, we can construct an infinite variety of sentences. So in that sense, English literature is separable because it has a finite and countable number of building blocks. Another example, music. If I take music constructed by piano, then in a piano you have these separate notes which are finite and distinct and countable that can be used to create an infinite variety of music. So the music from piano is separable. But on the other hand, the music from violin is non-separable because in the violin, we can create an infinite range of notes based on how much the violin string slides back and forth. And therefore, we cannot reduce the music created from a violin to a countable set of notes. So therefore, the music coming from a violin is non-separable. Same goes for the image created on this mobile screen or a TV or an LCD screen. It is created from a collection of primary colors. So therefore, the building blocks of this image in your mobile phone that you're looking at right now is essentially finite and countable and distinct. So therefore, this image is made up of separable colors. But on the other hand, if you look at painting or if you just look outside your room and see a landscape, it is filled with an infinite range of colors and wavelengths associated with those colors that we cannot sort of count in a distinctive manner, so it is non-separable. I hope you understand what we are dealing with. In quantum mechanics, most of the quantum mechanical systems are separable solutions. Why? Because whether you look at an infinite potential well, whether you look at a harmonic oscillator, whether you look at a hydrogen atom, you have distinct countable eigenstate solutions, and a general solution can be written as a linear combination of those distinct countable eigenfunction solutions. Therefore, in quantum mechanics, we have this additional property of separability. However, if you go to quantum field theory, separability is not satisfied for quantum fields. So these are the important criteria of what a Hilbert space is, and because quantum mechanical wave functions or quantum mechanical states belong to Hilbert spaces, they all satisfy these properties, and we will be using these mathematical operations, inner products and various kinds of properties associated with it in our coming lectures. Now, for those students in India who are preparing for all these different kinds of examinations, we have some very exclusive courses in our platform elevateclasses.in. If you guys are interested, you can check out our website. We have currently a live batch going on for NET and GATE students and an upcoming JAM batch for all the college students who are preparing for MSc entrance examinations. If you are one of those students, you can browse these courses, and if you decide to study and prepare with us, you are most welcome to do so. Now, I hope that by now you must have understood that out of all these examples that I've taken, these examples are examples of Hilbert spaces. Square integrable functions, 3D Euclidean vectors, complex numbers, real numbers, they are all mathematically and technically correct examples of Hilbert spaces. So that is all for today, guys. Thank you so much. I'll see you next time. This is Divya Jyoti Das from For the Love of Physics. Take care. Bye-bye.